All right. Well, welcome back, folks. Hopefully, you had a chance to take a look at the video yesterday. I didn't ask you to do too much yesterday with the video, but you're able to watch it and understand then the direction we're headed in. So, going into the weekend, then what I'd like to do then is go through a few more, talk about kinematics a little bit more, and then go over a few more of the problems for you and work through a few of these problems with you. And then what I'll try to do is over the weekend, and I apologize, getting these packets together has been a little bit more difficult than I had anticipated. But like I said, I will get practice packets ready for you so that you can work on this, so that we can get to free fall next week. And that way, then there will be a FET lab, finally a hands-on activity that you can do involving free fall and projectile motion. So we'll talk about that. I'll have a little activity planned for you with the free fall, and then the FET lab will take a look at then the projectile motion that we'll get started with next week as well. Okay. All right. So we were talking about these equations. We can come up with these equations here by basically taking what we know about acceleration. We saw then with acceleration, we saw what it was. Acceleration is basically defined then as a change in velocity over a given time interval. We saw then that if we rearrange that equation a little bit, we get this one here, which is the first of our kinematic equations that we'll be working with. And so with these kinematic equations, essentially what we're doing is that we're taking this equation, what we know about acceleration, essentially, and combining them together, rearranging equations, combining them together to come up with specific equations that we can use to analyze motion. Analyze specifically the type of motion that we've been talking about, which is motion in one direction, in one dimension, with constant acceleration. And that essentially is the study of kinematics. Kinematics is the study of motion in one dimension with constant acceleration, with no regard, without considering the forces that act upon an object. Because with constant acceleration, remember, what we're saying then is that the net forces cancel out. So if we have an object undergoing constant acceleration, remember, we keep this in mind that the acceleration doesn't change, but the velocity is constantly changing. Okay, so if the acceleration is not changing, no force is acting upon it. So, or the net force acting upon it's going to be zero. So that's why we can say then that with the study of kinematics, we are specifying then motion in one dimension, motion in one direction, with no forces acting on it because we're dealing with constant acceleration. Okay, all right. So we came up with this particular equation here, but just a simple rearrangement of the definition for acceleration. And then we were able to solve for a problem like this. And this is what we left off with yesterday, okay? By first of all, identifying what we were given, identifying what we're asked to solve for, picking the corrective formula that will allow us to solve for the unknown, and then rearranging that formula to get the equation that we will use to solve for the unknown. And so the method that we would use to solve for this one then, as we saw this, the method that we would use to solve for this one requires us to, and it helps us to organize the information, requires that we just draw a simple diagram and then to highlight and to point out what we have, what was given to us in the problem. Okay, so there's our diagram that we've drawn out. So we start out with a simple diagram where we label what we know. Okay, so we know then that the object is from rest. So we go ahead and we identify that here. Okay, so we label what we know. We know that the acceleration, they give us the constant acceleration here. And then they also tell us that it reaches a final velocity here of 28 meters per second. And so what they're asking us to solve for then is how far the object, how long was the object moving, how long was the car moving to get from one velocity up to another. Okay, and so we were able to identify the formula that gave us that. And so this is the formula here. So the formula here, remember, was the simple taking the range. Let me go ahead and write this out for you. We took acceleration, okay, which was defined then as the change in velocity, which is v final minus v initial, all over a given time interval. T from now on, remember, represents time interval, rearranging it to get v final here. Okay, so with this particular formula, okay, which would give us v final, really doesn't answer the question for us because we're solving for time. So we took this formula, rearranged it, and make sure you practice doing this. And if you are, if you're uncomfortable rearranging these equations, brush up on your algebra and make sure you do so. Okay, and so we rearrange this equation here to solve for time. Once we have the equation that we need, because time is all by itself, we plug in the values that we were given, and then we can solve for the unknown. So with all of these problems that we'll be doing moving forward, folks, all these problems that we're doing moving forward, we will only be solving for one variable. So that means then we should be given everything else. You just have to make sure you identify it. We should be given everything else. You just have to make sure then that you identify what you're given and then solve for it. Okay. All right. So with that said, what I would like you to do is let's work on this problem here. Let's take a look at number 9 in from your from the lecture here. Number 9. Let's work on this here, and then take about 5 minutes to work. About 2 or 3 minutes to work on this. I don't think it should take you more than that. 2 or 3 minutes to work on this, and then we'll get back together, and then we'll work on this together. Okay. So go ahead. Let's work on this here, and then we will. I'll work it out for you. Okay. So take about a few minutes to work on this problem. All right, let's go ahead and let's take a look at what we have here. Let's identify what we're given first. Okay, so make sure then I'm just going to highlight it for right now. Okay, let's go ahead and identify what we're given. We are given, if you look at here, we are given a speed. Okay, we're told then that the bus is moving at a certain speed. Okay, and it speeds up, which means then it accelerates, and we're given the acceleration here in as 3.5 meters per second squared. And we were given a time interval here. We're saying that 6.8 seconds later. So we're given a time interval of 6.8 seconds. And so therefore, what we are solving for then is we are solving for velocity. So what is the velocity? That's what we are solving for. Okay. So let's go ahead then, and let's draw our picture. Let's go ahead. I'm going to give myself a blank screen here, and let's write out what we have. Okay. So let's go ahead and work this one out together. Okay. All right, so I'm going to draw a simple picture for us. Okay, so we have then our object. I always want to start out with a simple picture. Okay, so we have our object here. There is our school bus. Okay, it's moving in one direction. Okay, it's moving one direction. At some point in time, it reaches a new position because it is accelerating and it is moving. Okay, at some point in time, it is going to be at a new position. Okay, all right. So what do we know? We know then that we are given the initial velocity. So let's go ahead and write that down. We are told then that the initial velocity is 30 kilometers per hour. Okay, so it's moving at that. We are told then that as it moves, it accelerates. So we can write down the acceleration here. It has an acceleration. It's going to move then. It's going to speed up at a rate of 3.5 meters per second squared. Okay, so we know it's speeding up here because the acceleration is positive and velocity is positive. Okay, so we know that as well. Okay. Furthermore, we are told then that as it moves for a time interval. So we consider this t initial as being 0 seconds. At some time final, at some time final, the time then is 6.8 seconds. Okay, so the time interval here, t then is going to be 6.8 seconds. We can always assume that with all these problems here, at the very beginning, that's going to be representing time 0, and that the time final is actually the time interval itself. Okay, so here the time interval is 6.8 seconds. Okay, all right. So we know these 3 items. We know the acceleration, that's what's given to us. We know the initial velocity that's given to us, and we know the time interval that is also given to us. Okay, and so what we are solving for then, they ask for is v final. Okay, so we are solving for v final here, and so this diagram here, instead of having to create a list, which you can do if you want to, you can draw a simple picture here and then list everything that you know and identify what you don't know here. Okay. All right. So with that said, then we have one equation that we have so far. The equation is v final is equal to v initial plus a acceleration times time. Okay. So this is the formula that we were given to describe then final velocity. The final velocity given the acceleration, time, and initial velocity. Okay, so the question then is, does the equation here, the way it's set up, give us v final? And the answer is yes. So you can leave this formula exactly the way it is, and then you can start plugging in your values. Okay, so that means then this formula here is already set up for you to calculate for v final. So leave it as it is. You don't have to arrange it at all. Okay. All right, so what the question then is this. Okay, so we have the initial velocity that's here. That is 30 kilometers per hour. We plug it in here. That's initial velocity. Okay, we have the acceleration. The acceleration's here at 3.5 meters per second squared. We plug it in right here. And then time that's given, or the time interval is given to us, and we can plug it in right here. So it appears then that we should be able to just plug and chug, folks. Plug in the numbers, punch away in our calculator, and get an answer. Okay, but there's a problem with this. And there's a problem with this, and I think that if you forgot to do this, if you did not recognize this when you did this, you will have an issue with your answer. Your answer will be wrong. And the problem is this, folks, and that is this here. The velocity is in units of kilometers per hour, and the acceleration is in units of meters per second squared. Okay, and so this brings me to a point that I need to make sure we address here, and that is whenever you work out these problems, all of the units must be the same. Okay, all of the length units must be the same units. All of the time units must be the same. And if the units for length and the units of time are not the same, you have to do what's called a conversion. And so I'm going to do this really quickly for you. If you have any questions on how to do the conversions, please make sure you keep this in mind. Come by and see me. But basically, a conversion is a mathematical tool that we use. It's a tool that we use to change units so that we have equivalent units. Okay, and we take advantage of relationships that we know about already. Okay, so before we get started with that, let me just point out to you here. So the unit of length here is kilometers. Unit of length here is meters. Okay, so we have kilometers here and meters here. They're not the same. So we have to, our first conversion, I'll do this in red. The first conversion has to change kilometers to meters, or we can go the other way if we want to. Okay. Secondly, if you notice here, the unit of time here is hours. Unit of time in our acceleration is seconds, and so we have to change that as well. We have to change the hours to seconds. Okay. So remember, in order to do this work, the units have to be the same. The length units have to be the same. If they're not, the problem won't work out correctly. The time unit has to be the same. If not, then it will not work out correctly at all. Okay, so this is what we have to do before we even plug in our numbers in order to get our final answer. Okay, so let's go ahead then, and let's do this conversion. Okay. Well, we start out here, and I think most of us know this, okay? And that is we need to define the relationship between these two length units. And we know this, okay, that for every 1 kilometer, that is equal exactly to 1,000 meters, okay? We also know this from common knowledge, okay? Well, okay, let me take that back. We live in the United States, so we don't use metric units. I think most of us, you've been through science, and even even if you haven't taken science here, in your other classes, you've had to deal with metric units before. Okay, so this is the equivalent metric units. If you don't recall this, or if you haven't seen this before, please come by and see me and get extra help with this. Okay, all right, but this we all do know. Okay, and that is we know what the relationship is between hours and seconds, and that is for every 1 hour. Okay, we know then that is equal to 3,600 seconds. Okay, all right. So we can take advantage of this here. These are two relations that we can take advantage of in order to do our conversion. Okay, and so the conversion starts out with this. We can either convert the meters and seconds to kilometers per hour, or we can convert this kilometers per hour to meters per second. I think the conversion that I'm going to do for you here is kilometers per hour to meters per second. Okay, so this is the method we're going to use here. Okay, so we're going to start out by we're going to set up a simple problem here in which we have a ratio. This is a unit ratio, folks, which tells us that it's 30 kilometers over 1 hour. Okay, and that's what we have. Okay, and so when we do this conversion here, we're going to basically set up fractions here. Okay, so we want to convert this into units of meters over seconds, over 1 second here. So we're going to convert the ratio, one ratio into another ratio with different units now, but they will be equivalent. Okay. Again, make sure you come see me if you're not quite clear on this. I think about 3/4 of about half of us in the class have done this before, whether you had science with me before or science with Thessaloniki, but we've done this before. Okay. All right. So with that said, then we can take this particular equality here and we can set it up as a fraction. Okay, that means then we can set it up as a ratio. Okay, as 1 kilometer over 1,000 meters, or flip it around, take the reciprocal. We can set it up as 1,000 meters over 1 kilometer. Okay, now I can tell you this, and we can take advantage of that. Those two fractions, those two ratios, are actually equal. They are equal. They are equal because we said then, we have defined then that these two sides are equal to one another. Therefore, these two will, this ratio here and this ratio here are equal because both are equal to 1. Okay. And again, we're going to take advantage of this relationship here. If you're not quite sure how we get this, folks, come by and see me. Same thing holds true down here. We can set up two ratios for this one. It'll be 1 hour, 1 hour, over 3,600 seconds, okay, or 3,600 seconds over 1 hour. And I can say then, in the same way that we said up here, that those two ratios, those two fractions equal to one another, and both of those are equal to 1 as well. Why that is, come by and see me, folks. It's a simple algebraic proof that we can use for that, okay? All right, so why did I bother to do this here at all, okay? Because what we want to do then is, if you see here, what we want to do is we want to change this kilometer unit to meter unit. We want to change this hour unit to second unit, okay? So with that said then, if we set up the problem this way, so what we're doing then is we are going to multiply by fractions, okay? We're going to multiply by fractions, okay? So let me go ahead and let's deal with the kilometer unit first here, okay? Which one of these fractions here, either this one or this one here, we will use. We can't use both. We're going to use only one of them, okay? But the one we choose then will allow us to cancel out this unit and leave this unit in the numerator. So of these two fractions, of these two ratios here, which one will have the unit meter in the numerator, and we need kilometer in the denominator, remember, in order to cancel out this here, this unit kilometer here. And we've noticed then that it's this particular ratio here, okay? And if we plug it in, and we'll plug it in right here, okay? If we plug it in exactly the way it is here with 1,000 meters on top and 1 kilometer on the bottom. Let's go ahead and take a look at that unit first. Notice here, this is kilometers divided by kilometers. When you are dividing by the exact same thing, you end up with 1. Okay, so when you take kilometers and you divide it by kilometers, you end up with 1. So therefore, we've essentially canceled out the unit of kilometers. Okay, so I'm going to go ahead and so we've canceled out the unit of kilometers. And if you notice here, then we have the unit meter on the top here in the numerator. Okay, remember, we're looking at the numerator. This is just one big long fraction. We have now meters in the numerator here and nothing else. So we got the number here, but the unit is meters. Okay, so there it is. Now we have the meters in the numerator. We have effectively changed the unit of kilometers, this length unit, to unit of meters. Now we still have to do the math. We're not quite done yet. Okay, we have to do the math, and then we'll get that done. Okay, we have to do the same things for the unit time down here of hours. We have hours in the denominator here. We want to change it to seconds. And so with that said, then we're going to go to the fraction, the ratio that it deals with time. And so we have two fractions that deal with time, and very much the same thing. We're going to do very much the same thing we did with the length unit here, and that is we need to change the hours to seconds. So of these two fractions here, which one has seconds in the denominator? And if you notice, it's this one right here. Seconds is in the denominator here. And so what we're going to do then is we're going to plug in this fraction here into our big long fraction here. So we're going to plug it in with 1 hour on the top and 3,600 seconds on the bottom. Okay, and if you notice here, again, just like we did here, this unit hour is in the numerator. This unit hour is in the denominator. Those two, when they will cancel each other out, and you're left with 1 as well. Okay. All right, so if you notice here, what we've done in the end, what we have in the end here is that we have then unit of meters with the left on the numerator, and that's only, and it the same as this fraction. We want to make sure the fractions are the same. We have seconds on the bottom here, and we have seconds on the bottom here. So we have just completed what's called a unit analysis, and this is part of a larger method that we use known as dimensional analysis in order to carry out these conversions. Okay? All right, so with that said, we're not quite done because we still have to make sure we plug in the numbers and deal with the numbers here. Okay, so let's go ahead and let's plug in the numbers really quickly. So now then we have in the numerator, we have 30 and we have 1,000, and we're going to multiply those two together. And on the bottom, we have 1 times 3,600. Okay, so we have now then 30,000 over 3,600. So right now, the equivalent to 30 kilometers per hour is 30,000 meters over 3,600. But we can use that if you want to. At this point, we can plug it in, but that's a huge number. So we want to simplify it. We want to make sure we simplify. So let's go ahead and simplify here. And so in simplifying, we just go ahead and reduce those here. Let's go ahead and plug that in really quickly. So 30,000, let me plug that in. 30, 1, 2, 3, divided by 3,600. I get 8.3. Okay. So we'll write a fraction out of this one, okay? So it'll be it won't be a whole number. It's gonna be 8.3 meters over 1 second. So now we have reduced, we have it in roughly a reduced form, and I want to finish up with this one, okay? So this here, this particular value is exactly the same as 30 kilometers per hour. That's what this whole conversion business is all about, okay? And so now if you notice here, we can use this number here because it represents the same velocity as what we have here, but it has the same units here now as the acceleration. So the length unit is meters and the time unit is seconds. And so let me finish here. We can plug it in. And so it's this here. It's this velocity we're going to plug in, not the initial velocity that we were given here. Okay? And for one simple reason, the units aren't the same. Okay. Okay. So let's go ahead and let's plug it in. We have then now we can go ahead and solve for v final. Okay, v final then, and the initial now we're going to plug in is 8.3. It's going to be 8.3 meters per second. Okay. Plus the acceleration here is 3.5 meters per second squared. And we're going to multiply that by the time of 6.8 seconds. Okay. All right. So plugging in all those numbers, we end up with our answer then as 32 meters per second. And that's going to be the final velocity. And that's our answer. And so what I would like you to do, okay, what I would like you to do to finish up here then is I want you to take this particular velocity here. So that's our answer meters per second. But since we started out here with a velocity in kilometers per hour, what I would like you to do then is I would like you to take our answer, 32 meters for every 1 second, and I would like you to work backwards and find the equivalent amount, velocity in kilometers per hour. And so what I would like you to do to finish up this problem is I want you to work out this problem here. I want you to do this conversion. What I'll do is then on Monday, I'll give you a quick primer. I'll review conversions here because I think this may be new for about half of you. Okay, so we'll practice a few more conversions. Okay, and then what we'll do is we'll continue on with our discussion of the kinematic. Okay, so finish up this conversion here. Try your best with it for those of you who are new to this. And for those of you who are well aware that have done this before, this should be pretty simple. So I want you to go ahead and do this conversion here. Okay, what then will be the answer in kilometers per hour? And we'll start up with this one on Monday. Okay, have a good weekend, folks, and I will see you on Monday.